Hi! I've gotten so many requests to do this one because it's making its rounds on Twitter and the Facebooks yet again. Nano diamond self-charging batteries could disrupt energy as we know it. What's that you can smell? Yeah, marketing bullshit. So thanks to everyone who copied me on their tweets and their Facebooks and their emails and everything, and linked in this article and other articles about, it's just hit the news again. Everyone's talking about it. This NDB, or Nuclear Diamond Battery Inc. Corporation. It's a startup company who have claimed that they're going to revolutionize the energy industry as we know it with these nuclear diamond batteries. And of course, there's nothing new here before at all. We saw this back in January when the University of Bristol and other places were all talking about hyping up these nuclear diamond battery powers. And at the time, Thunderfoot did a bust-in video on this. I'll link it in up here and down below and at the end if you haven't seen it, and he goes over the whole, like, all the physics behind it and the safety and the power output and everything else. There's just a ton of stuff in there, so watch that. I won't recover like almost anything that he's covered in here, so I won't touch like any of the physics behind any of this because we don't need to debunk this thing. Yes, I know I've got a lot of tabs open up there and we might eventually get to a lot of them, but hey, I'll save you the time and effort of watching most of this video. If you just want the quick skinny, you don't even need to read the article. You don't need to go to the company's website, watch any of their presentations, analyze any of the other information whatsoever. You can bust this by just looking at the photo in the article here. And here it is, NDB Inc. 100 microwatt Betavoltaic battery, model B7001 NDB Inc. USA nuclear diamond battery. Look, it's the size of, you know, a typical dip chip like this, right? There it is. 100 microwatts. That's the mu symbol. Microwatts. Yet somehow this could disrupt energy as we know it. Microwatts. You know how many applications there are for products that need microwatts of power? Yeah, not many. But these nano diamond batteries, they will blow energy density comparisons out of the water. 28,000 years without ever needing a charge. They'll offer higher power density than lithium ion. They'll be nigh on indestructible, totally safe in electric car crashes. And in some applications like electric cars, they stand to be considerably cheaper than current lithium ion packs due to their huge advantages. 100 microwatts is going to revolutionize the electric car industry. Now here's the interesting thing. I think the company slipped up because if you actually go, you search their website thoroughly, you even search the archives of their website, you can't find this image anywhere, yet it actually comes from them. Because, why? Why can't you find it anywhere? Please link it down below if you can, because it's actually got a number on it, a quantifiable number, 100 microwatts. That gives you the power output of this betavoltaic battery. And of course, betavoltaics are nothing new. 100 microwatt betavoltaic batteries are nothing new. City Labs, they've been doing it for 15 years. You can just buy commercial off the shelf. There it is. City Labs, 100 microwatt betavoltaic battery, the model P200. No worries, nothing new here at all. I'll even link in these City Labs promos down below. So yeah, these things are a real thing. In this case, they use tritium instead of, you know, this nuclear diamond thing, which we won't even go into the physics of it. I don't care. It doesn't matter. The fact is that these are basically energy harvesting devices, and we'll get into why they're claiming all of this marketing BS in a minute. And betavoltaics, suitable for low power, robust applications, nanowatts through to microwatts, power burst via secondary trickle charging, milliwatts to watts. And this is where this new nuclear diamond battery comes in. Look at this, a tiny nano diamond battery that's going to change the world. Hundreds of years of lifetime, safe and unbreakable, 7 times charge size versus current phone batteries. I don't quite understand that. Tiny and modular, can be sized to any device. It's a 14.29 times. You might think that's little tiny decimal point there. Little marketing trick, like whacking a tiny decimal point and putting lots of significant figures. So it looks like, at a glance, 14,029 times more efficient than radioisotope generators that are used in like deep space probes and things like that. Because once you get that far out, you can't rely on solar power. So you've got to have these nuclear generators. It's 14.29 times more efficient, you say. Well, okay, let's go to a radioisotope thermoelectric generator, which they use in space probes. Let's look at the plutonium-based version. We're talking about 0.54 watts per gram. So multiply that by 14.4, and we're talking about 7.7 watts per gram. By that sort of metric, what efficiency means, I don't know, but okay, it's 14 times better. Okay, so 7.7 watts per gram. Why does this just have 100 microwatts for a dip-sized chip? Marketing never adds up. So right there, right off the bat, using the company's own image for their Betavoltaic battery here, they've put this figure in which you can't find anywhere else, 100 microwatts. We've got a quantifiable number we can work with. So if we take this, chip, it's roughly, this one's a slightly bigger, but the volume, let's just go for volumetric efficiency, shall we? The volume of this thing, I'm going to say roughly equivalent to a AAA battery, okay? Just work with me. 100 microwatts. That's going to be like its maximum power output. And as we saw, there are other ones being commercially available for like a decade, 100 microwatt Betavoltaic batteries, right? So let's look at a AAA. So 100 microwatts, that is the maximum power that this thing can generate. Sure, it can generate it for a long time. I have no doubt it does it for, the hundreds of years or whatever they claim. Okay, fine. I'm not going to get into the details of that. But 100 microwatts is not capable of generating any more instantaneous power than that. Now, if we go and have a look at a AAA battery, a data sheet here at 1 milliamp constant current draw, so let's just call that roughly 1 milliwatt, right? A milliwatt is 1,000 microwatts. It's already generating 10 times that, but it can go for 1,400 hours at 10 times that. Now that actually works out to a capacity in a AAA battery at low currents like this of typically around 1.8 watt hours for an alkaline battery. Let's get out our confuser here. 100 microwatts times 24 hours times 365 days a year is, in 1 year, this little Betavoltaic battery can produce about 0.8. Well, 0.87 watt hours. So basically, their little pissant energy harvesting Betavoltaic battery here, whiz-bang nanocarbon technology, can only generate the same power as a AAA over 2 years. Sure, as I said, it can do it longer, but for the same volume, it's like a AAA battery for 2 years. What? And this is going to disrupt energy as we know it? We're going to be able to power, electric cars and phones and all sorts of things with this thing? No, it's bullshit. It's busted right there. All of these claims are just startup marketing wankery. And this is why I guarantee you, go and look through their website, and nowhere on the website, even in the archives, I searched things. And mysteriously, by the way, all their app presentations, their presentation fact sheets are mysteriously missing from their website. Why? Just like this image is missing from their website, because it contains a number on it, a quantifiable number that people who, if they actually did a few basic calculations, would be able to show that this thing is never going to disrupt the energy market, because it has only niche application in ultra low power devices. So yeah, you don't even have to go past the first image supplied by the company to know that everything else is just a complete hyperbole. And by the way, nowhere on the website, nowhere on the web at all, can I find any evidence of any prototype of this thing. There's no photos, there's no data, there's no output power, there's no characteristic curves, there's nothing. The best we've got is this dip-sized chip that says 100 microwatts on it. Whoop-de-doo, you've been able to buy those for a decade. Look at this, it's got graphene, of course it's got graphene. Graphene's the buzzword of the decade for startups. And so it's got a 3D supercapacitor to store the charge. Aha. A phone that will never run out or need to be recharged ever. Oh, read more. Best life battery phone. I don't think I've even looked at that one yet. And look at all this marketing wank. Seriously, like I won't go through it all. It is just all we're going to target, augmented reality, smartphones, tablets, game consoles, self-powering CPUs, virtual reality, smartwatches, wearable tech. Our target markets are all these companies and come on. Anyway, what we're interested in, this 1.5 volt, look, 1.5 volt AA nuclear diamond battery. And they even tell you on the webpage here, if you care to read, the nano diamond generates and harvests electricity. It's an energy harvesting system. When you hear energy harvesting, you know it's little bitty, teeny weeny. Oh, by the way, they claim here, what makes diamond unique is that because it is an excellent charge collector, near 100% efficiency, it can collect almost all of the charge generated, meaning it's incredibly efficient. Oh yeah? Let's go over to this TechCrunch article here, which just came out. I couldn't find the press release for this, by the way, because their press release page doesn't actually have this. But obviously, TechCrunch got a press release, self-charging 1,000-year battery startup. They claim that they aced their key test and lands first beta customers. Okay, they've aced their testing. You would think they'd have data in here. So these tests took place at Lawrence Livermore National Lab and the Cavendish at Cambridge, and both NDB's battery tech managed a 40% charge. I don't know what that means. I assume that's 40% efficiency. It was a big improvement over the 15% charge collection efficiency of standard commercial diamond batteries. So in their own press release here, they say, no, we only achieved 40%. But in all their other marketing stuff on the page, they're happy to talk up 100%, aren't they? Yeah. But look, it contains an advanced printed circuit board and a supercapacitor. Aha. And they tell you another reason why the battery has such a wide range of applications, like all the EVs and everything else they're talking about, is because it has charge storage. It's got a graphene supercapacitor in it. Of course it has. If you ever need to use a lot of charge in one go, even beyond what the nano diamond is producing, the whole 100 microwatts of it, the supercapacitor is there to make that possible. Oh, graphene, it won the Nobel Prize in 2010, so it must be good. And these supercapacitors, absolutely fantastic. Well, let's take a look at their AA battery, shall we? NDB AA, here we go. We've got a wanky video made from recycled nuclear waste. Made using nanotechnology. Sorry, it's a bit hard to read, isn't it? I don't know what they mean by this. In 1 hour, it's 100% efficient. Once again, they're assuming that 100% efficient is holding 3.5 times more charge than a regular AA. It's 53% smaller, identical in weight. What? For 100 microamp source. Anyway, here we go. Look, you can get different voltage outputs, and this is where their supercapacitor and their energy harvesting chip, right? Their energy harvesting boost converter here. Oh, look at that. I love the little, the way that the caps, like the surface mount components with actually through-hole pins on them. Anyway, wow. So it's a nano, like the 100 microwatt energy source, because that's all you'd fit in based on their own photo, fits in the bottom of that AA, and then they've got a tiny little supercapacitor up the top, so it can, yeah, look, I don't dispute that they can actually, they could probably make this, right? I'm not going to dispute that at all, and it'll, like, Okay, it'll be a AA that lasts forever. But the fact is, it's a one, based on their own photo of that 100 microwatt source, that's about the volume that you'd fit in the bottom of the AA. You know, a couple of hundred microwatts tops, even if they can do it in the cylindrical form factor, but let's just assume that they can, then that's your energy source. A couple of hundred microwatts maximum. How long does that take to charge a supercap to give a standard AA output capacity? Okay, let's go to a AA battery here. 5 milliwatts, 900 hours. We're talking about 4.5 watt hours in a AA, a standard size AA battery. So that's what it's got to emulate. So 4.5 watt hours divided by, let's be generous and say 200 microwatt, 200 microwatt generation. 22,500 hours. So your whiz-bang AA here is self-charged itself. Let's say it comes from the factory, it's pre-charged, it's self-charged, and you used up your AA capacity, you used up your 4.5 watt hours, you pissed it away in a day or two, and you want your battery to recharge itself from the built-in 200 microwatt source. Then, yeah, you're going to have to wait 22,000 hours for this thing to self-recharge. It's ridiculous. The reason that they're claiming all of these ridiculous claims is because presumably you'll be able to recharge the AA battery or the 18650 cell or whatever it is, that you'll be able to recharge this like a normal rechargeable battery. It's no different to any other rechargeable battery technology, but in this case, it's a graphene supercapacitor. The fact that it has this nuclear diamond battery in it, this little piss weak, couple hundred microwatt nuclear diamond battery, whoop-de-doo, it'll recharge in 22,000 hours. Oh, wow, this is going to revolutionize the entire energy industry, absolutely. So all these claims down here, it'll be able to produce 3.5 times more charge than the entire content of a typical disposable AA battery every hour. That is absolute bullshit based on their own, look, 100 microwatts source. Just run the numbers. A smartphone in just 1 hour, a 100% efficient, and even if they can get 100% efficiency, which their own press release says that they're only getting like 40%, will be able to produce 7 times more charge than the entire content of a typical smartphone battery every hour. Bullshit. Their own marketing image disproves their own numbers. No wonder they don't want to show that anywhere on their website or put any technical information whatsoever on their website. Go search through the whole thing. It's a very extensive website. I've used Google to search, like specifically target the site itself, trying to find presentations that have any resemblance of data in it whatsoever that shows you the power output from their betavoltaic battery and a nuclear diamond battery. It's a betavoltaic, whatever. And it's just not there because they don't want to tell you the real numbers. They just want to do like page after page of marketing. It's just, product competition. It's just like, here it is, right? This is why they'll only ever talk about energy density. Like, I have no doubt that it's 4,000 times more energy dense than gasoline. It's 56,000 times more energy dense than electrochemical batteries like 18650. Yes, it may be because you use a tiny amount of your diamond or whatever with your radiation they're very dense. Yes, but you can't get it out. Their own photo here, 100 microwatts. I keep going back to it. They've slipped up. They've released a number there. They've told you what this thing can actually produce in that sort of volume, 100 microwatts, just like the other betavoltaic batteries that we've seen here. So yeah, all their marketing is just going to be based on, energy density, and they can prove it, and they're right? I'm not even going to dispute that, okay? I haven't double checked, but hey, let's just run with that, right? It's 56,000 times more energy dense than lithium ion batteries, okay? And it's 16 times, here we go, 16 times more efficient than a typical betavoltaic. Okay, so if it's 16 times more efficient, why does the leading one on the market, the 100 microwatt betavoltaic from City Labs, the model PN200, let's just call it roughly the same size as their one here, 100 microwatts. They're both exactly the same number. in, you know, roughly the same package. Where's the 16 times? But even if it was 16 times, let's take that 22,500 hours again and divide that by 16. Oh, the AA battery's only going to take 1,400 hours to recharge itself. Yeah, great. And then they've got this timeline. It'll be implemented in 5 phases. Phase 1 is the opportunity will be identified. A business plan will be composed around the initial idea. And this company hasn't been going that long. So I think they're still on phase 1 or phase 2. We'll develop that idea both scientifically and business strategically by establishing the structure of the company that will develop the idea into a product. Sourcing funding develops initial. Yeah, that's what they're doing. They're looking to fund this thing. They've got nothing to show. There are no prototype photos whatsoever. There's no data at all. Because if this stuff really existed, they'd be publishing the data and money would be pouring in. But it's not. It's just your typical energy startup who just have to market in terms of, oh, it's X amount, 1,000 times more energy dense and all that sort of stuff. They don't get into the practicalities that this is an energy harvesting device. Phase 3 will outline the end of 18-month period. A formal review will be carried out to evaluate the process after 18 months. Phase 4 will then further develop into a prototype. They'll finally get to a prototype by phase 4. Where's the photo of their prototype? They're nowhere near. It just doesn't exist. Then they'll finalize the details and launch the product through feedback from beta testers. Oh, wonderful. And Nano Diamond Battery Organization was only founded February 4th, 2019. So it's been going for a year. No prototypes. Although they claim to have actually tested something at those labs. As you saw it got 40% efficiency. There's no power output stuff whatsoever. So yeah, they're just like, they're nowhere. And that's all their recent news. There it is, the TechCrunch article and that new Atlas article that's generating all the hype. And here's an article here just released. They're 2 proof of concepts. And once again, yep, they're saying like 40% charge, it's more than the 15% charge collection of previous ones or something like that. But like, there's nothing else. There's nothing else. Seriously, please, if you can find any data at all on this thing, link it in down below. And then they talk about device fabrication. Just go through the website. It's got everything you could possibly want, except any actual data. And you can look at the design of it and everything. And look, they actually talk about, yeah, it harvests electrons, basically. And look, the maximum amount of electrons it can harvest, 11,400 electrons. The mean, 3,600 electrons. It doesn't say what actual, size cell actually does that. But anyway, the ideal device, the ideal one could produce up to 1,000 electrons per decay with an average of blur electrons. So they don't actually say, but once again, go back to that photo, 100 microwatts for a dip-sized chip. And of course, the exact amount of current that it could yield depends heavily on variables such as device design, diamond purity, crystallinity, and size. So yeah, they don't tell you. There's no numbers anywhere. But once again, their own publicity photo, 100 microwatts in a dip size package. They've even got a product number for that. You can't find that product's just, the dip product has just mysteriously vanished because, well, you don't want people to know that it's just a pissant, betavoltaic generator, just like you've been able to buy for the last decade. But hey, we've whacked a graphene supercapacitor on it and we've got a fantastic marketing website and, well, the money's just going to flow in. Oh, yeah. And if you want a feel for how many electrons we're talking about here, 3,600 electrons per second, 1 amp. 1 amp of current. Imagine like an EV and how many amps it requires. Anyway, 1 amp of current, right, is like 6 times 10 to the 18. 10 to the power of 18 electrons per second. This thing, one junction, can generate 3,600. Whoop-de-doo! Then they talk about like capturing the function of the distance and things like that, you know, depth and stuff like that. So they're talking about they've got some thin film technology and stuff, have a large surface area to extract the current from, and they can fine tune the thickness of the diamond layer such that the energetic electron will generate most of the electrons near the collector's surface, can optimize the device output. Once again, they won't tell you. There's nothing. All we got to work from is the 100 microwatts. And down here, like they talk about conceptual diagram of a nano battery. Like these prototypes don't exist. They're talking about a titanium charge collector because they talk up the advantages of titanium over gold and stuff like boron doped ohmic interface. And like who cares? Without the actual data, it's all just useless marketing waffle. But they actually admit here, NDB is an emerging nano battery technology. This is due to the challenges in its execution of the design. Nano battery is a direct product of cutting-edge nanotechnology where atomic material manipulation is crucial. They need atomic material manipulation is crucial to generate their 100 microwatt dip size battery. They need experts to design and build it. Have too thick a layer of diamond and the electrons released will recombine, become lost in the diamond. Have too thin a layer and there's not enough diamond to release the electrons efficiently. I mean, come on. This is just all pie in the sky stuff. Yes, it works. As always, these things work in quote marks. And yes, they might be 10, 50,000 times more energy dense than lithium ion or some other, battery technology. But 100 microwatts in a package, thousands of hours to recharge a AA or AAA battery. No, it's not going to revolutionize anything. It's just all bullshit. Automotive, consumer, anything, space electronics, medical, aviation. It's just, no, these things they're no different, effectively no different to existing beta-voltaic batteries that you've been able to buy commercially for a decade. By the way, I think the going rate for one of these was a couple of $1,000s for one of these chips, which is great. If you have a very specific niche need for a super long-term battery, these are tritium-based ones. These supposedly don't last as long as these, whiz-bang diamond ones, even though they haven't even got prototypes of the diamond ones yet. These are 40 years or something like that. But still, great for really niche applications. But that's where it's going to remain. Niche applications. It's not going to disrupt energy. Anyone who invests money in this thing or spreads this thinking that it's going to change the world and, we're going to have nuclear diamond batteries in our EVs is just, no, it's crap. Look, 100 microwatts. It's done. It's dusted. This is energy harvesting beta-voltaic battery. The end. So anyway, hope you found that useful. If you did, please give it a big thumbs up. As always, comment and discuss down below and over on the EEVblog forum, and check out all my other pages. I'm on Library, I'm on Vimeo, I'm on BitChute, I'm on Dailymotion, I'm on my own blog website. I'm everywhere. Catch you next time.